We are going to wrap up Chapter 13 by talking about Le Chatelier's principle. And that's going to be looking at how these changes in concentration, temperature, pressure, and then gas volumes by containers, and then water volumes affect where the equilibrium lies and what's in the mixture. So here's concentration is the first one. If we add a substance A, that's a reactant, the equilibrium will need to adjust because that equilibrium ratio is not the same. We are going to shift away from that. We say shift to the right to get rid of the A that we added. If we were to remove A, we take some of that out. Well, we're going to, in order to get the ratio back, we just lost reactants. We need that products over reactants. We need that ratio replenished so the reaction will react backwards in order to generate more A. And we say it shifts left. Temperature is one where we're very used to looking at heat as a product or a reactant, so we got to do that again. This one is a product in the first example because delta H is negative 882. We consider it a product. Down here it's written as a reactant. It's just 25.69 plus this. It's on the reactant side written in the equation. And this delta H is positive. So we can see these either way. And then we want to see how this reaction will shift with changes in temperature. So the first one, if the temperature is lowered, in each case, if I lower it in A, that means I'm losing heat, which is a reactant. So our reaction will shift right to generate more heat. So the answer to the first one here, let's slide it over here. This one is going to go right. Now, temperature is the only one that actually changes the value of K. Okay? It changes the value of K. Since we shifted right and we didn't actually affect the molecules, we're making more products. What that is going to increase K. K is going to get bigger. Products over reactants. If I make more products, K is going to get bigger. In the second scenario, we cool this one down. We are removing a reactant. The reaction will respond by generating more reactants to replenish what was taken out. So this is going to shift left to generate more reactants, and then K is going to get smaller. Temperature is the only one that changes the number of K. Everything else just stays with the same K. Dry ice subliming, we can do this with a balanced equation too. So carbon dioxide, solid, turns into carbon dioxide gas. That's sublimation. That takes energy, so heat is a reactant in this one. It's endothermic to go in there. So again, if we remove heat, we need this reaction to shift left to replenish the heat that was lost, and then K will get smaller. When we talk about pressure, what we're looking at is the coefficients of the gases. So we get this strange question here. There's no changes yet, but it just says a shift to which side would contribute to an increase in pressure. So one point of clarification here. My balanced equation has a side, the right side or the left side. My reaction container does not have a side. It is a container filled with reactants and products in different ratios. And then if I shift one way or the other, well, maybe I turn reactants into products, and if I shift the other way, maybe I turn products into reactants, and then if I shift the other way, I turn reactants into products. So it's one container. We don't talk about sides of the container, we talk about sides of the balanced equation, right or left. It just means what do I have more of in the one single container. So in the container here, we look at this one, and we see my reactants have 1 mole of gas in question number 1, versus on my product side, I have 3 moles of gas. We're just keeping track of the moles and only the gas. So if I shift right, I will have more molecules, and more collisions and higher pressure, because pressure is collisions of molecules. That's what gas pressure is. So in this case, a shift right would generate more molecules and more pressure. It's not that the right side has more pressure, so we got to be careful with words. It's one container, but a shift right will increase the pressure of the one container. In the second one, I have 2 moles of gas on my reactants side and no gas on that one. So here, shifting left will generate more molecules and increase the total pressure of the container. In the bottom, I have 4 moles of gas on the reactants, and the products, if I shift right, I only have 2 moles of gas. So if the reactants are favored here, this will give me a higher pressure. If I shift to the left, I'll have more molecules coming from the reactants. Not on the reactant side, it is one container. Okay, very important. And we'll see the applications of that, because sometimes you have to make a decision. If you want the pressure to go up or down, you shift to the side of the balanced equation that generates either higher pressure with more moles, or if you need the pressure of the container to come down, you can shift to the lower side, which creates less moles. Water is very, very much the same way, except in a solution. So here we count the aqueous coefficients. In this example, we have 5 moles of aqueous particles on the reactant side and only 1 mole of aqueous substances on the product side. Okay, so here we actually get a question. What changes will take place if water is added? Well, if water is added, water is not in this balanced equation, but water is going to give me more room. So if I have more water, I have more room for stuff. So I'm going to shift to the side that allows me to have more molecules. So the first part of the question here, if water is added, well, that is going to cause this reaction to shift left, because the shift left will generate more aqueous particles, and they can dissolve in the water. What about if the water is boiled away? Well, now I have less water, so I don't have as much room in this scenario. So if I remove the water, now I'm going to have to shift right, because there's not enough room for the particles to move around. So maybe these 5 particles will come together and make 1 particle instead. Now they have a little bit more room because I've got 1 particle bouncing around instead of 5. So a shift in which side, right or left, will make my one container more or less crowded from how many moles of particles we have. Okay, so we can apply that all together here. Question number 1. If water is removed, so water is a product, I take out the water, then I need to shift right to make more. If hydrogen is added, then I've got too much reactants. I need to shift right again. Okay. The system is cooled. Well, here we need to know what delta H is. Their clue is plus oxygen. This is a combustion reaction, so heat is definitely a product here. So if it's cooled and I'm removing heat, I need to shift right to generate some of the product I lost. And this is the only one here, temperature changes, that it's going to make K larger. It'll change the actual number for number 3. Catalyst is added. Well, catalysts speed up reactions, but they're not going to affect the equilibrium position. We're going to have the same amount of reactants and products that we had before. It's just going to be a little faster reaction, so no change there. The pressure goes down. Well, for pressure, we need to consider the moles of the particles. Over here, I've got 3 moles of gas on my reactants equation, and on my product side, I only have 2 moles of gas. So now we need to think through this a little bit. If the pressure goes down, then we need to do the opposite. The reaction will shift to increase the pressure back up. Okay, so in order, we need the pressure to go back up. In order to make the pressure go back up, we need the reaction to generate more particles to bring that pressure back up. So this one, since the pressure went down and we need it to go back up to undo that change, we need to shift left. Okay, so this one is going to be a left shift for number 5. Volume is very similar. Let's kind of slide this up a little bit. Volume, the volume goes down, that's just a veiled way to say that the pressure went up. Okay, well, this is another pressure question. Now, if the pressure went up, we need it to come back down. The reaction, in order to get the pressure back down, the reaction will make fewer molecules. They'll combine together, so there's fewer things bouncing around in the container. This is going to be a right shift. Okay. Here's another set. What is going to happen if nitrogen is added? If I add nitrogen, we need to go to the right to remove the reactants that we added. If helium is added, helium's an inert gas, nothing's going to happen. If the container is made larger, that's a volume question. The volume is going to go up. That means the pressure is actually going down. We need to look at the coefficients. Here I have 2 moles on my reactant side, and I have 2 moles on my product side. So there's actually nothing that can happen in this one. It's just like, oh well, the volume got bigger. Because the moles, there's no way to change it and bring that pressure back down. Or to bring the pressure back up, because the pressure went down and we need it to go back up. We just can't do it. The system is cooled. Here we have the delta H is a positive 1.81 kilojoules. That means that heat is a reactant. So if I'm cooling it, I am removing a reactant that is going to shift left to generate more. And if I shift left, this is the only one that changes the value of K, temperature. If I shift left and I make more reactants, I am going to have a smaller K. Everything else, if I add, like in number 1, if I added more nitrogen, I already changed that ratio. The shift is just going to get back to that ratio. It's the same number, just to get back to where it is. Temperature is the only one that actually changes what the ratio is. Everything else just gets back to the same ratio, but we can't do that with temperature changes. A couple more, and these are a little bit harder here because they're kind of one step removed from the problem. Here's a problem that has a high pH. High pH is means it's basic. So we have a lot of base. That's as if we're saying, there's my sodium hydroxide. We need to look at properties of the substances in there. That's like saying I have a lot of NaOH. If I have a lot of NaOH, then we're going to shift to the other side to get rid of some of that NaOH. At a high pH, we're going to shift left for this example. If HCl is added, well, the HCl is going to react with NaOH, because one's an acid and one's a base. So this is a veiled way to say we're removing NaOH. And of course, that's a little harder to understand. They react, we lose the NaOH, but if I remove it, I need to shift right. So we got to be careful on how that's asked. Here we have another one. Barium nitrate is added, which also looks innocuous, and it's not in the balanced equation. But then they tell us that barium hydroxide is insoluble. That means it'll make it precipitate. So this is a veiled way to say that the barium is going to react with hydroxide, which is, in this case, it's going to be sodium hydroxide because it's aqueous and it dissociates. So this is another way to say remove the hydroxide, the NaOH. If we remove NaOH, we're going to shift right to generate a little bit more NaOH that was removed. So these are a little bit trickier. You kind of have to think about properties and side reactions that take place and how it affects the balanced equation. Last one, we can also look at properties of colors. How will a shift in pH affect this color? Well, pH is the measurement of the hydrogen, so here's my hydrogen. So a lot of hydrogen means a low pH, okay? So a low pH means a lot of hydrogen, and if I have a lot of hydrogen, I'm going to go left. But if I had a very high pH, that means I do not have a lot of hydrogen, and we would need to shift to make some more. We're going to shift right because I don't have a lot of hydrogen at a high pH. So that one would go right in that case. And then we can also look at how's it going to affect the color. Well, a left shift, if I'm going to the left, I'm going to get orange. But if I shift to the right, I'm going to get yellow. So a low pH that goes left, we should see an orange solution. And at higher pHs that shift right, we should see a yellow solution. Last question, how is diluting shift the equilibrium? Diluting is going to be adding water. If we add water, we need to look at the moles of the aqueous solutions most of the time, okay? Or, in this case, water is actually part of the balanced equation. So let's do it both ways. First off, we'll just do the easy way. If I add water, let's get rid of the All right, here we go. Nope, that's not going to work. All right, if I add more water, I should shift to the right. If we looked at the moles of aqueous substances, on the left we have 1 mole of aqueous particles, and on the right we have 4 moles of aqueous particles. So adding water is going to allow for more room for those aqueous particles to move around and dissolve. If I have more water and more room, we should also shift right just based on those coefficients, because now I have more room for the solution to dissociate and react with the water. So we should see this one, if I'm shifting right and I add water, we're going to see this one turn out to be a yellow solution. So Le Chatelier is kind of tricky. You just got to be careful. Remember, you're just talking about one container. But when we say shift left and right, there is no left or right side. It just means, am I making more products or reactants? If you read carefully, you can do really well in this section.